Good morning. I think it's in India, it's 12:30, so it's good afternoon, but in Germany it's 9 a.m., so good morning. My topic is satellite generated brightness temperature. Myself Mukesh from Department of Environmental Science and Civil Engineering, JCRC University, India, as well as Polska University, Olomouc, Czech Republic. This is my small biography. In my presentation, I will be explaining about introduction, motivation and objectives, data which I used, methodology, result and discussion, and in last, conclusions and perspectives. So first, what's the importance of land core classification and surface temperature? Actually, land use land core in terms of temperature and soil moisture affects surrounding climate such as water vapors, dust particle, gas molecules, and cloud formation. So it's directly affect to rain and rain effect to land use. So by this way, it's affect whole ecosystem. Again, timely monitoring of natural disaster is important for minimizing economic loss caused by flood, drought, etc. So it's important for emergency management during natural disasters. That's why remote sensing of land core classification and surface temperature has become an important research subject. In this presentation, I will be explaining about satellite generated brightness temperature, which is influenced by soil moisture and vegetation cover. Actually, I will be derive MPGR values and then classify land core classes. So my main object of this research work is derive MPGR values, use them for land core classification, which will be help to monitoring weather, climate, and natural disasters. So first, I want to talk about data. Actually, optical and thermal remote sensing data is greatly influenced by cloud cover, atmospheric water content, precipitation, making it difficult to collect accurate information in compare with microwave remote sensing data. But in other hand, passive microwave emission penetrate non-shifting clouds, providing a better representation of land surface condition under nearly all weather conditions. Actually, as you all know that optical and thermal data or visible data, they are affected by the atmosphere. But microwave data, they penetrate more Earth surface, working in all weather conditions in day and night times. So they will provide more information. That's why optical or thermal remote sensing data cannot be used to retrieve surface temperature during active weather condition. However, microwave remote sensing can overcome this disadvantage. And some other things like global data are available daily from microwave radiometers, where optical sensors such as Landsat, TM, ASTER, MODIS are typically available globally only as weekly products due to cloud. In this research work, I was using MSRE and MODIS data, which I got from NSIDC NASA Center. I use MSRE data because it's better than its previous microwave data, such as SMMR and SSMI data. If I talk about spatial resolution, it's just double spatial resolution and used all frequencies which is used by individually by SMMR and SSMI data. Here are few characteristics of MSRE data. It's 12 and 10 bit data. It has 6 frequencies, 6.9, 10, 18, 23, 36 and 89 gigahertz. Its highest resolution is 5.4 kilometer and lowest is 56 kilometer. This is a basic slide in remote sensing. Actually, we cannot collect information directly from our satellite data. So first we need to go through pre-processing like geometry correction, so that each pixel open its exact location on the ground, change detection techniques, image enhancement, band ratio, resampling. So they are increase the quality of data or satellite image for better interpretation than PC and supervised and unsupervised classification. So by this way, we convert pixel-based raster information into vector layer. So these steps come in digital image processing, and once we save in vector layer, it's saved in GIS module. This is a basic slide of remote sensing GIS, so I will not go in more details here. Actually, my research work, it means polarization ratio and gradient, so basically based on NDVI concept. NDVI means normalized difference vegetation index, and its value is from -1 to +1, and always high value is associated with a healthy vegetation or dense or good quality vegetation. Here NDVI means near infrared band minus red band divided by near infrared band plus red band. And these are few examples. If we use Landsat TM or ETM data, we use band number 3 and 4, and for NOAA, AVH, RRR and MODIS data, we use band number 1 and band number 2. As I told you, polarization ratio and gradient ratio is very much similar like NDVI concept. So here is the formula is same. The basic difference between PR and here is in polarization ratio we use same frequency, but it's both part vertical as well as horizontal. Here this is an example. If I use frequency number 19, it's 19 vertical minus 19 horizontal. But in gradient ratio we use two frequency, either it's vertical or horizontal. So this is an example. I use frequency number 6 and 10, but it's only vertical part, not horizontal part. Actually, MPGR values are effective indicator for land surface vegetation cover density. So here I put brightness temperature value in place of frequency. So if there is little vegetation cover, then optical depth can defined as a 0, and we can use emissivity in place of brightness temperature. And again, the formula is same still. It's place of brightness temperature I put emissivity. So according to Plomnia and Plosia, we can assume emissivity of soil is equivalent to emissivity of vertical plus horizontal frequency divided by 2, and constant temperature is equivalent to soil. Then the soil value or the object value is closer to the surrounding features. This is the resulted image after polarization ratio and gradient ratio. This first image is polarized image after 36.5 gigahertz frequency. Here you can see that the values, if PR values are increased, it's so high temperature. So I can say here that the values are associated one side with the land use land cover classes and another side is temperature. Because if the values are increased, it's so desert area on the globe, and if the values are down means it's colder effect and it's so green vegetation or vegetative part, and in between it's in between classes. And again with the help of PRGR we separate out land and water. So on the basis of MPGR values we can classify our land cover classes. Actually NASA my chief want to know three things: which frequency is so actual physical land surface temperature, as MSRE data has 6 frequencies. So which frequency is so actual physical land surface temperature? Second, he want to know the behavior of each land cover classes, and third, which combination of MPGR are best suited for land cover classification. And for that I just simply overlap MSRE data with MODIS data. MODIS data was 17 land cover classes data and its standard product, and then take sample set for one sample set for each class. So MODIS has 17 land cover classes and I take 17 sample sites from MSRE data. By this way I just capture the brightness temperature value from the MSRE data and then derive maximum, minimum, mean and standard deviation value for all horizontal and vertical frequencies, and to determine which combination of MPGR are best suited for land cover classification. And this is all 70 land cover classes which is so by the MODIS data with their codes. So 0 code for water, starting codes for forest area or vegetation, like 13 is built up, 15 is snow and ice, and 16 is bare soil. So this is my first resulted slide. And as I want to know the which frequencies of actual physical and surface temperature, so here we can see the result. This is the frequency number 6.9 horizontal. These are all 17 land cover classes, and this is the temperature in Kelvin. So these so the maximum, minimum, mean, and standard deviation value. Here you can see that the water is showing 100 Kelvin temperature, ice showing around 250 Kelvin temperature, bare soil is little bit less. So I can show that I can say that water is not or never colder than the ice. So this is not so actual physical and surface temperature. Now I will compare with the same frequency 6.9 gigahertz, but its vertical part in place of horizontal. Here you can see that water come downside water, so around 20 ice so less than 200, so it's better than the horizontal frequency. Now I compare with high frequency and low frequency. It is the high frequency of 89 gigahertz horizontal. Water is goes around 230 Kelvin temperature, ice is go below 190 Kelvin temperature, bare soil also about 270, built up area also about 270. So I can say that this is so very close to actual physical and surface temperature, and the comparison of between low and high frequency means high frequency is better than the low frequency. Now again high frequency, but it's vertical part. And the all classes of actual physical and surface temperature. And water is about 250, ice is very cold, bare soil is about 300 Kelvin temperature. Here I want to say that means vertical frequency is better than the horizontal frequency and high frequency is better than the low frequency. But if we want to classify only forest area or vegetation part, we can use low frequency. But for water, ice or bare soil, we must be use only high frequency. So here as we find out that vertical frequency is better than the horizontal frequency and high frequency is better than the low frequency. Again, low frequency are hardly influenced by atmospheric effect during bad weather condition, but they are affected by surrounding features or background subjects because they are absorbed less and scattered more by soil. And high frequencies, they are influenced by the atmosphere than other frequencies. So second result which I want to know the behavior of each land cover class. As in graph you see that evergreen needle-leaf and broadleaf forest have higher temperature than deciduous forest, but both forest type have lower temperature than shrub and so on. Mixed forest has a much smaller range of standard deviation and always falls between evergreen and deciduous forest. Close shrub has lower temperature and a smaller standard deviation than open shrub, and wetland has lower temperature than grassland and cropland due to water content. You will see that 70 land cover classes in the graph is sort in different place. And in last, built-up area has higher standard deviation than other land cover classes except for water and ice. Third thing I want to know that land cover classification on the basis of MPGR values. So for that I make three combinations. PR means polarization ratio, PRGR and GRGR means gradient ratio combination, and make two plots for each combination. So this is the first graph or first combination for PRPR. I use frequency